Hello, I'm Hannah Bausch, and I work with Steve Jacobson in his mineral physics lab. And I'm studying the physical properties of ferropericlase at core mantle boundary conditions in order to investigate ultra-low velocity zones, which you can see here in red. And there are zones atop the CMB where P and S wave velocities are up to 30% slower than the surrounding mantle. And they're also 10% denser than the surrounding mantle, but we don't know why. So some people think that higher iron concentrations in these zones could play a role in why we see these lower velocities. So I'm going to be performing shock ramp experiments of ferropericlase, varying the amounts of iron and performing them along isotopes relevant to Earth in order to see if these iron defects could help explain the slower sound speeds that we see. Now, in preparation for the experiments, I'm performing density functional theory calculations to predict how ferropericlase will behave during the experiments. Density functional theory simplifies the calculations for studying atomic structures by using atoms' cloud density rather than the entire Schrodinger equation. On this pressure temperature plot are some of the results from calculations I've done on 20 mole% iron ferropericlase, along with the geotherm for reference. The principal shock eugonio describes how a material behaves under shock compression due to thermodynamic relations. So consequently, we are able to learn how our material behaves at high pressure and temperature conditions, like the core mantle boundary, for instance. You can see that the principal shock eugonio shown here in blue actually lies below our area of interest around the core mantle boundary. So I also computed a preheated shock eugonio shown in red, aiming to get closer in temperature to the core mantle boundary. In addition to the shock eugonios, I also computed a quasi-isentrope, which predicts how ferropericlase will behave when the material is ramped rather than shocked during experiment. Traveling along a quasi-isentrope is great for us because we can get direct measurements of sound speeds of ferropericlase under relevant conditions that apply to the Earth's core mantle boundary. Here in orange, I computed a quasi-isentrope that starts from an initial shock and then ramps with the intention of probing to pressures near the core mantle boundary around 135 GPa. A shock ramp path like this is ideally what will happen during experiment. While I've been performing these calculations, I've also been synthesizing MgFeO samples for the experiments. First, I mix the powders of MgO and hematite, pop them in a furnace at 1300 degrees Celsius in fugacity conditions within the Wüstite buffer zone for 24 hours, drop quench the samples so that they cool quickly in a controlled environment, crush, grind, and press the pellets again and put them all in for another 24-hour round. So we get well homogenized ferropericlase powder that we'll use for polycrystalline samples for shock experiments. And that's what I've been doing over the summer. Thanks.